talking about variation in the patellar tendon moment arm identified with an improved measurement framework. Total knee arthroplasty demonstrates excellent survivorship and pain relief. However, extensor-related problems remain common. The patellar tendon moment arm, the PTMA, is a measure of the mechanical advantage of the extensor mechanism of the knee, and its proper description may make it a more effective design target in arthroplasty. PTMA measurement has several challenges, notably including definition of the tibiofemoral rotation axis. The instantaneous helical axis is the most accurate choice, but requires calculation of tibiofemoral velocity, often achieved by differentiating noisy, optically tracked positional data. When velocities are close to zero, for example near full extension, the IHA is undefined, and differentiation excessively amplifies noise. Experimental constraints like prescribed tibiofemoral velocity mitigate noise-related errors, but are physiologically inaccurate. Data smoothing may offer a solution, but has not been fully applied to the PTMA. This has produced a confusing body of PTMA reports which often contradict reported anatomical differences. For example, whilst the PTMA has been consistently reported as relatively constant between male and females, trochlear geometries and quadriceps force generation, both of which are likely to affect the PTMA, have been found to be different between the sexes. So, conclusions about the PTMA remain uncertain. We first sought to determine a data smoothing technique that minimises PTMA measurement error using optical tracking, facilitating our second aim of assessing PTMA variation in the native knee. To optimise data smoothing, a model reference knee was fabricated. The PTMA was physiological in length and known throughout extension. Mechanical stops ensured tibiofemoral velocity was zero at full extension and flexion. Before PTMA calculation, optically tracked kinematics were subjected to 4 smoothing techniques. Data were first left unprocessed, then were separately Butterworth filtered and spline interpolated. Lastly, data was smoothed using combined filtering and interpolation. To avoid subjectivity, all smoothing processes were automated, and the effectiveness of each approach was assessed by root mean squared and maximum error compared to the reference. Use of unprocessed kinematics resulted in large errors in PTMA calculation. Filtering improved accuracy in the mid-range of motion, but large errors remained near full extension and flexion. Spline interpolation enabled accurate measurement at the limits of motion, but errors in the mid-range remained over 1 mm. Combined filtering and interpolation reduced error to below 1 mm over the entire range, crucially including terminal extension and flexion. To assess PTMA variation in the native knee, 24 fresh frozen cadavers were dissected, and the quadriceps, ITB and hamstrings were loaded to a total of 225 newtons, distributed relative to each muscle's cross-sectional area, with tensions directed physiologically by pulleys. Joint kinematics were tracked from 110 to 0 degrees of flexion, using the same protocol as the fabricated knee. The native PTMA was calculated using kinematics smoothed by the established combined filtering and interpolation approach. The resulting trajectories were duplicated. One set was left unscaled, and the second was scaled by epicondylar width, reducing the effective knee size. Pearson's correlations between the PTMA and knee size were calculated. Both datasets were split into male and female groups, and differences were assessed using t-tests. The native PTMA increased during extension, peaking around 20 degrees, and then reduced until full extension. Before scaling, the male PTMA was significantly larger throughout extension. Knee size explained most of the variation in PTMA magnitude, demonstrated here by the high correlation between peak PTMA and epicondylar width. Size scaling eliminated all magnitude differences between the sexes, however shape differences were maintained. We examined where the PTMA peaked in extension, which was inherently unaffected by scaling. Peak PTMA occurred 14 degrees closer to extension in female knees, with extremes at 1 and 37 degrees of flexion. These two extremes are shown here after size normalization, demonstrating the large variation possible between two PTMA trajectories. In conclusion, we have found that combined filtering and interpolation enables sub-millimeter PTMA calculation accuracy over the entire range of motion. Axis approximations and non-physiological constraints are not necessary when using modern motion capture. The framework would also suit in vivo approaches like mobile fluoroscopy that does not suffer from limitations unavoidable in vitro. Knee size explains most of the variation in the magnitude of the patellar tendon moment arm. However, the overall trajectory is size independent, demonstrated by the 14-degree difference in location of peak PTMA between the sexes. Relocation of this peak could significantly depower the knee during critical tasks like walking. This highlights the importance of patient-specific biomechanics in designing arthroplasty and musculoskeletal models that might otherwise only consider size. Aided by improved accuracy, future work might fully assess the role of morphotype or examine the PTMA during functional activities. I'd like to thank the following for their involvement in the study, and thank you all for listening.